In this video, we are going to learn how to design and detail the reinforced concrete shear wall, which is a part of building frame system. The situation given is shown: FC prime 6 KSI, FY 60 KSI. The building is a 30-story building. The slab is 8 inches thick. The beam has a cross section shown, columns cross section shown, which will be displayed on the layout. The seismic zone is 2B, soil SD, and the importance factor is 1 for seismic. Building frame system. The loads are shown which will be applied on the slab. Wind speed configuration. We have to calculate the shear wall thickness for the whole building and design reinforcement of shear wall 5 using Etabs and cross check plus design reinforcement on Excel. Detail the Etabs output in AutoCAD, wind and seismic load using UPC 97, and the design code is ACI. The plan is shown. We are required to design the shear wall number 5 as shown in the plan. So we can see the corner exterior columns have a different size. The theoretical background for the lateral force resisting systems types commonly used are: number 1, moment resisting frame. It is a structural system with complete space frames for support of gravity loads and resistance to lateral load by the flexure action of the beam, column, or the frame members. The second is the building frame system. It is a structural system with essentially complete frame providing support for gravity load, and the lateral load support is provided by shear wall or brace frames. The dual system, which will be discussed in the next video, the lateral loads is provided by shear wall or brace frame, and moment resisting frame takes 25% of the base shear. So in order to model the building frame system in Etabs, we have to consider the following steps. Since we want lateral load for the seismic and wind to be carried by shear wall alone, so we modify the flexure capacity of the columns using property modifiers as 0 or taking negligible value, making columns flexible. While in first model we will use property modifier for the wall as 0.7 and check on ultimate combinations for the shell stresses using envelopes. If exceeds modulus of rupture, then modify the modifier as 0.35. For design of frame members, we will use another model having columns modifier as 0.35 or 0.7 depending on the cracked or uncracking condition for the column. The detailing of column and beam in building frame system is carried out using special conditions for the special moment resisting frame. Starting with the Etabs modeling. Number of grids in X direction. Starting with defining the grids as we were given the condition. So we have modeled the grid system. We will start with defining the material properties of concrete, that was 6 KSI or 6000 PSI. Modulus of elasticity can always be checked by 57000 under root FC prime. The compressive strength is 6000 PSI. Now adding the rebar material, that is grade 60, G60. Also check the material property data, 60,000 PSI rebar. Now we will go to define the frame sections. Let's just delete the useless cross sections which we don't require in our model, which will further create hassle. So we will be deleting and then adding our cross sections required, starting with the column section, adding the material for the column. It is just for application of the mass of the column, as we are taking its flexural strength negligible, since we want all the shear force to be taken by the shear walls independent of the columns. The columns will, however, resist the gravity loads as mentioned in requirements of the building frame system. Adding the second column property. Now delete this property. Adding the periphery beams properties. In building frame system, we usually have periphery beams only, no internal beams, as the lateral force resisting system of shear wall is independent of the frames, as we want to transfer all the lateral force to the shear wall. So now we will be defining the beam properties. So now frame members are defined. The next step will be defining the slab sections, which we were given as 8 inches thick slab, material for slab is same as the used. The property modifiers for slab conservatively is taken as for the flat plate slab. Property modifiers for moment of inertia. Now adding the property of the walls. For walls cracked and uncracked condition, initially taking 0.7 as per ACI uncracked section requirement. The modulus of rupture is 7.5 under root FC prime, that is 6000. If the stress using envelopes will exceed 580 psi, then we will change the modifiers to 0.35 for walls, for force and membrane bending. For initial iteration, we will take the modifiers as 0.7 for the walls. We will add different thicknesses for the walls, having a 3 inches increment every time. Usually we play in 3 inches terms for the formwork. You can also take increments of 2 inches or simply 1 inches, but since it is a high-rise building, so we directly take the increments of 3 inches. Now defining Etabs auto select option, so that Etabs picks the cross section itself accordingly, adding the list of the sections from which Etabs will select. Median by thickness means Etabs will start from the least thickness to the required thickness. Now we will model the structure, starting from modeling the columns. It is the model of a complete building frame system. For dual frame shear wall design, the next video will be updated on that topic. The dual frame modeling is different from building frame modeling, so stay tuned. Now drawing the columns of the other cross sections as we were shown in the plan. Modeling the beam in the layout. As already told that there are periphery beams in the building frame system essentially. Usually no internal beams are present in the building frame system as the external moments or the lateral force resisting system has to be independent from the frames. Now modeling the shear walls, and the type of area is pier. So the shear wall is drawn on the story, that is 30th floor. Now we will draw the slab, that is 8-inch thick in our case here. Yes, so we are done with modeling the slab. Essentially we are done with modeling the single story of the building we were given, whose plan was basically shown in the beginning. So now we will proceed to the next step, starting with pier labels. As we were shown the labels of the walls, wall number 2, wall number 3 to wall number 6. Now turn off the visibility of the members other than the walls so that the selection is easy and assigning piers will be faster. Now assign the shell pier labels. This one wall is the wall number 1. Then wall next to it in horizontal direction is wall number 2, as we were shown in the beginning of the video. This is wall number 5. Then here we have wall number 6. Similarly wall number 3. And then the wall number 4. Now you may change the visibility of the font size, so it's extra large. Now I will revert or just make it some adjusted font size. Let's take it as 8. This is 10. So now you see we have to design the wall number 5, but the thickness is to be designed for the whole wall of the building. So now we have to define the load patterns. Defining the seismic load cases, earthquake in X and Y direction, whose conditions are given to us using UPC 97. Earthquake in Y direction, earthquake X drift, in order to check the drift, earthquake Y drift, and the wind. Wind load will also be added using UPC 97. Now we have to replicate the modeled structure to the rest of the height of the building. Now we have to assign diaphragms to the structure on story level. So diaphragms are now assigned. Edit the automatic mesh. The maximum meshing size for the meshing shall be taken as 3 feet for the accuracy purpose. We have assigned the automatic mesh in Etabs. Now going back to defining the load patterns. In earthquake X direction, the soil type and the zone was given to us. Now we will go to UPC 97 code and look for the factors value. Seismic zone factor is 0.2. The coefficient of acceleration and coefficient of velocity. Etabs will automatically pick these values for CA and CV, while for CT it is 0.02. Since it is not a moment resisting frame anymore, it is a shear wall system with moment with a frame. For building frame system and concrete, the value of strength reduction factor is 5.5. The value of CT is 0.02. The value of R is 5.5 as shown from UPC 97. So now we are done with defining the parameters of application of linear static load in X direction. Now we will assign the similar properties or parameters in Y direction, just the difference will be it is in Y. So CACV automatically selected by software, and the value of our strength factor is 5.5. Now for the drift load cases, take the parameters as they are. The difference you will see in the later part of the video. Soil type SD and the zone is 2. Lower strength factor 5.5 Actually, mistakenly I have added the wind load in seismic terms, so I have to delete this and add the wind load in wind load category using UPC 97. Now we have to modify the load, the seismic speed, the wind speed, and the source. Exposure type 0.8 inward and 0.5 outward of the leeward and the windward wall condition for our case, which is already defined in the wind load case by default by Etabs. Now you may see the diaphragm D1 extension to different stories. Now we are done with defining the wind load pattern in Etabs. The next step would be defining the load cases. Now you can see that I want drift cases not to be considered in design, as I will amplify the drift cases to inelastic conditions. Since the drift ratio limit is applied on inelastic drift, so in order to convert the elastic drift, that is by reduced base shear, we multiplied by 0.7 times R. That the scale factor in our case will be 3.85 as shown. We have to incorporate the scale factor, that is 3.85 times amplification of the drift load case, and that is the reason we don't consider it in design. EX and EY will be considered in design, while EX drift and EY drift will not have to be considered in design, and they will only be used for checking the drift limitations according to the code, that is UPC 97. Now defining the mass source. So the dead loads will added with a multiplier of 1. For live load, as you all request in the previous lecture, what will be the live load factor and its reference in the mass source. For the live load, we considered the code ASC 7-05. The section 12.7.2 mentions that a minimum of 25% of the floor live load in public garages and open spaces can be considered. So conservatively, we can take 25% of the live load in the mass source, and the reference is already shown. Usually we do this in high-rise structures. Since it is a 30-story structures, so we are considering the height. Since the column and beams are in zone 2, so they will be designed using intermediate moment resisting frame. In this video, our concern is not design of the column and beam, so just for the transfer of forces purpose, we selected the particular option. In order to apply the vertical component of seismic load, we take SDS value as 2.5 times CA. CA, that is based on UPC 97. We will take this value as 2.5 times CA, that in our case it will become 0.7. So in other design cases we will also apply the same thing. For shear wall design, the value of SDS as 0.7. You can also change the rebar material, but it's already 60 KSI assigned as default. No need to change in slabs. Now define the load combinations using concrete shear wall. Convert to user editable so that we can define the envelope later on. Let's check whether it has taken drift load case or not. Since it has not taken the drift load case, which is okay, as we don't want the building to be designed on the amplified drift case, which is only for the drift check. Now defining the envelope so that we can check the maximum stresses due to different combinations in the wall. If they exceed modulus of rupture, we will have to modify the wall modifiers as 0.35. Right now we have taken the modifiers of the wall as 0.7, which is of uncracked section using ACI code. I will repeat that whether if the stress using envelope exceeds the modulus of rupture, that was 580 psi discussed in the earlier part of the video, then we will have to modify the moment of inertia or the bending moment capacity as 35% of the gross section in place of 70%, which is defined now. That will automatically consider the walls as cracked when the applied load will be in action. Now we will be assigning the loads to the slabs. The lab load was 40 psf as specified in the question or the situation, and the super dead load was 36 psf. Now the P delta options based on the loads. So the reference for P delta live load will also be provided. You can see in Etabs website, if the building code requires the load combinations which is shown, a P delta combination of 1.2 times dead load, which is already taken, and 0.5 times of live load is conservative. So we will take 0.5 live load multiplier, and the reference is already shown. Usually we do this in high-rise structure, similar to the addition of 25% load case of live load in the mass source. And the reference are all shown here. So we'll make the bottom of the columns and the reinforced shear wall as fixed. It is all on the designer whether he want to take pin supports or the fixed support and design the footing accordingly. Now we will run the model. So I am speeding up the model recording speed. Since the running process takes a lot of time as it is a high-rise structure, so the speed is enhanced 32%. Now we will click on the shear wall design. So it will design the shear wall piers. Since auto select option was selected, so Etabs will now show which cross section it has selected in terms of thickness. Then we have to reanalyze assigning those sections not using auto select option. First we will see what sections are selected. So we turned off the other elements visibility apart from the wall. So for instance, we can check the view color of the object by the section. So the thickness selected by Etabs here is 15 inches. Let's check what's the thickness here. It is still 15 inches selected by Etabs linear static analysis. The thickness is still 15 inches. We will do couple of more iterations. Turn off the grid system visibility. Checking a bit higher section of the wall. It is still 15 inches. Thickness of the shear wall taken by Etabs. The design of shear wall by Etabs itself has selected the thickness. So the overall thickness taken by Etabs is 15 inches. You can also click on show sections on the Etabs option and click on undeformed shape. So you can see all of the walls are showing a thickness of 15 inches as selected by Etabs using auto select option from the list of walls which we defined in auto select list. So now we will unlock the model and manually override all the wall as 15-inch thick so that it is designed accordingly. Now we will have to rerun the analysis and then the design. Since design is an iterative process, you have to do iterations, so there is no need for a hurry. The design must be safe, following the requirements of the codes, plus economical. So amplifying the speed of the analysis, making it 32 times fast. Now we will start with the shear wall design using Etabs option. Now the walls are designed. We will check whether steel is not exceeding at least 1 to 2%. So which is quite easy to place, and the minimum percentage of flexure reinforcement in shear wall is 0.25%. So the reinforcement is wall is quite high, that is 1%. So it is a high reinforcement in shear wall. So we can revise the thickness of the shear wall if we want to. The required reinforcement percentage is 1% coming out as per the thicknesses selected by Etabs itself. Let's go for the bottom story, which we are supposed to design right now. The required reinforcement is 0.45. Let's say it is okay for now. Rather, if we were supposed to design the whole wall, we have to revise thickness, which we will do in this video. So it is important to do various checks while making the thickness calculation. So as you may remember that we had to check the property modifiers whether 0.7 is okay for the wall or not. The time period of the structure is shown, which will be useful in the drift checks. Let's check the displacement of the story on the thickness assigned. Let's click on story drift. It will display a list of story drifts and the condition will be applied. Since the time period is greater than 0.7, then a drift limit of 2% will be applied using UPC 97 code as discussed in the seismic drift check video in this same course. You can visit channel to check out that video. So we will sort the drift. But since we have to first uniform the modifiers of the wall, so we will check the stresses in the wall. If we were to reduce the modifiers, then the time period of the structure will change as well as the drift. So first checking the shell stresses, and the limit of the stresses was 580 psi, which was told in the starting of the video. So you can see stresses are exceeding in the bottom part here. Exceeding the 580 value somehow, as the purple color shows. Let's check the normal stress, that is S22. It's not as low as it seems. It is exponent 3 times. So you can see it is exponent 3. That means 1.0 here shows a 1000 value. That is 1000 psi, and it definitely exceeds 580 psi limit. So we will give it a try by revising the thickness or increasing the thickness from 15 inches to 18 inches. And till which height we have to increase the thickness of the wall, we can check it right now. Wherever the stresses are lower than 580 psi, we will revise the thickness of the wall till that portion in order to continue using the modifiers as 0.7. It is always desired to continue using the modifiers as 0.7. For that we have to control the stresses value below the modulus of rupture. First we will try reducing the thickness to increasing the thickness, and if not so, still not under control, then we will have to use the modifiers. Let's give a try increasing the thickness till the height. First we have to hide the rest of the walls, hide the selected walls, and the thickness to be increased are of the walls shown whose stresses were higher than 580 psi. So we have to increase thickness and try whether the thickness will affect the stresses and will it make the stresses in control. Let's rerun the analysis and check. If this will not control the stresses exceeding 580 psi, we will have to finally modify the uncracked modifiers to cracked modifiers, that is 0.35 in place of 0.7. So increasing the speed of analysis to 32 times. In the beginning of design we have seen that the steel was nearly 1%, so that increasing the thickness will also help us in reducing the amount of steel, which is already helping us with that. But the thickness should also be controlled. It should not be high enough by the design. So now you can see by viewing the properties of the objects, the thickness are different here. So viewing the elevation of the section which we have to design of the shear wall number 5. Now we need to check whether the stresses are exceeding the modulus of rupture, that was 580 psi. The highest stresses were axial stresses, so we will check those stresses. As the scale shows and the color shows, the stresses are still exceeding the modulus of rupture, that is 580 psi, and the power is exponentially here. So now we will have to finally change the thickness, change the property modifiers of the wall to a cracked section, and then we will check the time period for drift checks. Since the drift was within the limit of lower thickness, so it will definitely be within the limit of a higher thickness, but we will check the drift limit on revising the modifiers and the finalization of thickness. So the stresses are still exceeding. Here the stresses are tensile stresses, as the blue color is tensile stresses, which is definitely exceeding modulus of rupture. So for modulus of rupture we have to check the tensile stresses exceeding the limit. Now first save the model as it is slowing down. Now go to define wall sections. Properties for the walls and change the property modifiers from 0.7 to 0.35 for all the walls. whichever we defined. So quickly changing the modifiers of the walls from 0.7 to 0.35 for all the walls which we defined used in this model. Modifying all the walls property modifiers because we may mistakenly assign the particular wall and submit the model for wetting. So we are, in order to save from that mistake, we have to change all the modifiers to 0.35 and keep a uniformity in the model. Now run the analysis part. Again speeding up the analysis. Now the thickness of the walls are finalized plus the modifiers of the walls are finalized. Now we will calculate the reinforcement of the wall and then detail the shear wall in the next 5 minutes. Now click on design of the wall. Now shear wall reinforcement limitations. Using ACI code (2014). Conservatively for horizontal, that is shear reinforcement, and for vertical, that is longitudinal or main reinforcement, the minimum limit is 0.25% of the cross section, which we will be doing using Excel sheet. So we were required to design the shear wall number 5 of the bottom story, and the same procedure will be carried out for design of rest of the panel of the shear walls. So in order to save time, we just have to design one wall in this video. Now hide rest of the walls. You can first display the reinforcement. Sometimes it so happens that whenever we go up, the steel increases. So select the highest amount of steel for the bottom part. So the steel is reducing as we go up. We will be changing the font size in order to enhance visibility. So this is the Excel sheet whose link is given in the description for downloading. The thickness of the wall is 18 inches. The length of the wall is 60 feet of the whole panel of the wall, that is shear wall number 5. The length we have to assign is for this single pier, that is shear wall number 5, and the pier is shear wall 5. The length of the wall should be taken same as the length taken for the pier, which is 60 feet in our case, and the units shall be in millimeter square as per requirements of the Excel sheet. So the wall is in elevation number C. We will go to elevation number C since it was a 3D view. Now you can see from in it the steel units is in millimeter square required in this pier of the wall, that is shear wall 5. The steel is decreasing as we go upwards, except in one place. The highest steel here we get is 32,000 something. So we will enter the value in millimeter square as 32,588 and the diameter of the bar, which is our choice to select. The required spacing is shown. The red color is the input and the green color is output in this Excel sheet. We will provide the spacing of 200 mm. The Excel sheet will check it from the minimum, that is 3 times thickness, 18 inches, and the length of the wall divided by a factor. The least spacing criteria is OK. So the main steel to be provided is die 16 at 200 mm center to center. Now we go to the horizontal or shear steel. Note that you can also check the percentage of the shear or the main reinforcement. Let's click on the Pier reinforcing ratios. From this same sheet you can cross check whether we have provided the minimum steel in the wall. So you can see the minimum required steel is 0.0025 and the provided reinforcement ratio is more than that. Also it is shown on Etabs that the steel required is satisfying the requirement of the minimum steel. Now we will go for the shear reinforcement, that is horizontal reinforcement in the wall. It is in millimeter square per meter. The unit should be as I am showing. The steel is uniform here, that is 1143, so the highest value is 1143 for the bottom, which we will input in the sheet since we are required to design the ground floor only. So let's select the same diameter of the bar, that is dia 16. So the required spacing is about 350 mm. Let's take 300 mm, so it is OK with respect to minimum requirements and the required spacing. The theoretical background is also stated in this sheet. Hence it is displaying the horizontal reinforcement detailing as well. Now we have to detail this in AutoCAD. The reinforcement which we have designed using Etabs is to be detailed in AutoCAD. The drawing cross section of the shear wall is prepared here. We are using a 16 dia bar or number 5 bar simply for the main and the distribution or shear reinforcement both. It is important to know that in case of walls thick than 10 inches, we have to provide 2 layers of reinforcement. As you can see, we have provided 2 layers of reinforcement, that is on interior face and exterior face. And in case of walls less thick or thinner than 10 inches, you can provide single layer of reinforcement as required. So the Excel sheet is only for single layer of reinforcement. Since the design and detailing of reinforced wall is complete, you can also check the stability limits for. It is important to check these limits since it is a high-rise building. Due to seismic load and wind load, the drift and the torsional irregularity. Since it is a high-rise structure, therefore drift due to wind and seismic is important as serviceability check. Also the torsion irregularity will be required to check whether the building is not flexible in the direction. We have to check the calculated story drift it shall not exceed 0.025 for structures having period greater than less than 0.7 and 2% for period buildings having period of 0.7 or greater. So first we will check the time period of the building. As we have revised the thickness, we have to do the checks. So the time period is 3.564 seconds, greater than 0.7 seconds, hence the drift limit is 2% for our building. So now we will do the respective drift check for the building. Go to analysis, results and displacements. Go to story drifts. Click on OK. Now we will have to apply the earthquake drift combinations which were amplified to inelastic drifts and the limits of the code applied to inelastic drifts which were enhanced by 0.7 into R to make them inelastic. So the load case is and combinations will be used using earthquake except for the wind. Now sort descending so that the highest value appears on the top. The highest value is less than 0.02. That means the drift is in control. The highest value is 0.19 nearby. So the drift value is in control for our case. For checking wind drift limitations, usually in practice it is taken as drift ratio 0.25% for the buildings, that is L by 400 to 600. The ratio of maximum story displacement and floor height shall not exceed 0.0025 or 0.25% in other words. So selecting wind and the drift, and the maximum drift coming out is less than 0.0025, hence it is in limit. For torsion irregularity, the maximum deflection at corner of the building shall not exceed 1.2 times of the average displacement. So we go to story minimum divided by average displacements. The value shall not be greater than 1.2. The ratio is sort descending, so the highest value is 1.208. We will assume for now that the value is within control. For controlling this value, you have to increase the stiffness of the structure or the thickness of shear wall. The value 1.208 is very near to 1.2, so we will ignore that. As the loads are already factored enough. So for viewing the detailing preferences in Etabs, although we use AutoCAD for that purpose usually, since we selected all the bars to be number 5, we will go, and the minimum splice length is 60 times diameter of the bar usually. Go to detailing preferences and set these values, and rebar selecting rules, detailing preferences and the units in FPS system and the weight in ton. For the walls we have already set these parameters. Now we will go to the rebar selection rules for the walls. As we have selected diameter 16 in horizontal and vertical reinforcement for our detailing, so we will use the similar detailing here so that we can view the 3D view of the reinforcement cage. You can also get an idea of the Etabs detailing and drawing sheets. Selecting all the bars as number 5 since we used diameter 16 bars. In other words, diameter 16 is number 5. It is just US naming and the other is MKS system naming. So selected number 5 bar for the case. Now we will go to 3D reinforcement cage views. Or start first that for that first we have to start detailing the structural drawings according to the preferences we have set. Now it will complete within a couple of seconds. Since we have designed the wall only, so the detailing first shows the layout plan for the wall. The section haircut is section B and the section haircut is section A. The detailing sheets would have included these sections in elevations or section cuts. Since our reinforcement wall was, you can first check what is Etabs taking the name for the reinforced shear wall number 5. First save this just in case to speed up the process. So we will search for the wall reinforcement layout. You can also edit and arrange or drag it to fit the sheet which looks appealing. So the wall which we designed was reinforced shear wall number 5. Etabs is calling it as F2. And this is F3. So we designed the wall F2 and F3 is here. We can also check the reinforcement cage views. Let's have a look on the reinforcement elevations. CWF1, which is not our case. We have designed the reinforced wall CWF2. Which is here. So you can see the location of lap splices from Etabs detailing option. It is also useful to somehow get a knowledge about the detailing of the wall. Now we will check the 3D view of reinforcement in Etabs. Let's for instance CW4. This is the reinforcement 3D cage view for the wall. It is important to note that you can also check for lap splices in the wall here. The Etabs detailing preferences helps you with checking the lap splices. You can see the lap splices are visible over here. Upon zooming, they become more clear. So this was the shear wall design and complete detailing using AutoCAD and Excel sheets. plus the analysis carried out and the calculation of thickness using Etabs. In the next video, you will see the complete design of the reinforced concrete shear wall, which is part of dual frame system. Thank you for watching.